Hello, we're Team 9, and for our final project for EX568, we're presenting autonomous parking in an unknown dynamic environment using the CARLA simulator. So here's some background and motivation. Autonomous parking is one of the most vital ADAS systems that is becoming very popular nowadays. And in this task, there are dynamic unknown environments which the vehicles must navigate. Many of the open source solutions that currently exist often oversimplify the problem or ignore things like non-holonomic constraints and dynamic obstacles. So in this paper, we overcome these assumptions using the ROS integrated CARLA simulation platform. So more formally, here's the problem statement. From an arbitrary starting position in a parking lot, the car searches for an obstacle-free path to the provided parking spot and completes the parking maneuver autonomously. We take the following assumptions. The dynamic objects are only walking pedestrians. The goal, coordinate, and orientation of the parking spot are known, and that there exists at least one open spot. What you see on the right are the figures of what our parking lot looks like in CARLA, and below is kind of representation of our problem statement.
Yep. So now I'm going to talk about the proposed method. So like I mentioned, we are using Color to work on this project, but we also integrated the SLAM toolbox and hybrid A-stars into the Color system using a rows bridge. So we also use rows because that simplifies our coding and development a lot. And in the scenes, this is the particular scenes we're working with. There are static obstacles and also dynamic obstacles like walking pedestrians. As for the path planning, we're using the hybrid A-star algorithm, which is basically just an extension of the A-star algorithm, and it uses two heuristic to calculate the best path from the starting point to the goal point. The first heuristic is just calculate the best path, but ignore all the obstacles along the way. The second heuristic uses ridge chips to respect the non-holonomic constraints of the car. So using this algorithm, we actually will be able to find the best path from the start point to the goal post while respecting the non-holonomic constraints of the car. So I'll park on it to Max.
Yeah, so I'll be talking about the SLAM system we'll be using. So for our SLAM system, we're using SLAM Toolbox, which is a LiDAR-based SLAM method that relies on pose graph estimation using odometry data and LiDAR scans, which we can take straight from CARLA. And the CARLA has the integrated LiDAR sensor, which has noise with it, and also odometry from the wheelbase. And then with SLAM Toolbox, it'll build a 2D occupancy grid that represents the surrounding objects, and this is easily interfaced with ROS through an occupancy map variable. And then once we have this constructed occupancy grid and vehicle pose, those are passed into the hybrid A star to actually path plan to the goal pose that we set. So here's a little demonstration of just our path planner and SLAM method in action. We can see the vehicle moving and path planning to a specific goal location next to this car on the right side. And as it goes, it'll constantly update the path planning as the map is updating in real time, just to account for any dynamic or any obstacles that the LiDAR sees in the environment. Yeah.
Yep.
So now we move on to actually addressing how we're going to plan for dynamic obstacles. So how do we avoid the pedestrians in the environment? There's two different scenarios. One is a dynamic pedestrian where we actually wait for the pedestrian to pass out of the way from the vehicle and not make any weird maneuvers that might scare the pedestrian. And then there's the static pedestrians where we actually consider them an obstacle and path plan around them since they may just be waiting for another car. And that brings us to first, how do we even detect these pedestrians? And what we can do is actually use segmentation. So by segmenting our LiDAR point cloud, we can determine what points in that point cloud correspond with a pedestrian. And once we know that, we can correctly figure out if they're dynamic or static. And we can do this through the CARLA semantic LiDAR, which is already built into CARLA, but in real world situations, we'd use some sort of LiDAR segmentation algorithm. So here's a simple pipeline of how our pedestrian avoidance actually works. We extract the semantic LiDAR point cloud and mask out the points labeled as pedestrians, and we then transform them into the world frame, which will then be used to calculate how far they change from one scan to another. And we make them in the world frame so we don't get their movement relative to the car, but relative to the actual global world. Once we have this distance, we can check if it's greater than zero point 0.1, we mark them as dynamic. And if they're near the vehicle, we'll stop the vehicle. But if they're not dynamic, we just make sure that they pass into the SLAM system to get used in the occupancy grid. So here's an example of that. We can see as the car is moving forward, the pedestrian that is moving is not being registered into the occupancy grid. And then once it's in front of the car, it'll stop, activate the emergency brakes, and then it'll keep moving while the other static pedestrian is actually being considered as a obstacle in the occupancy grid, as you can see in the bottom right. And it'll continue to reroute around that.
For the evaluation, we conducted 8 different experiments, as can be seen in the image below. We set 2 different goal positions, and from a common initial starting point, we ran 4 different test cases. The first one is a static scene with no dynamic object. The second one is considers a dynamic object, in this case a pedestrian that is moving along the way of the car. The third one is a static pedestrian that is within the way that the car moves. And the fourth one considers the static pedestrian and also the dynamic one. We run 8 different drives for each test case, and we average the results for our metrics. So the results we got from our test is that for the parking average position error, we got very good results. We are within, for most of them, within 0.5 meters, and the same for the average rotation error. We also measured the localization and path planning error. So since we have the ground truth position of the car, we can also compare to our estimated post. And as can be seen in the first and second column, we did quite well where our position estimate is within 20 centimeters of the ground truth. We also take into account the path length, the average speed, and also the time taken, which is dependent of the complexity of the test. As can be seen in these images that represents the different test cases for each different experiment that we did, we can see that, for example, for the first column, where no dynamic object is present, the car follows a very simple route. But by the time we add dynamic pedestrians, as can be seen in the second column, the car has to stop for a bit to wait for the pedestrian to go through and then continues its trajectory. In the third one, since the pedestrian is static, the car has to replan and to follow a trajectory that avoids the pedestrian. And for the fourth one, something similar happens too. Future work, we would like to actually do parking spot detection, since right now the parking spot is a given position. It's known all the time. We will also like to test different SLAM methods, for example, visual SLAMs methods, or even fuse information from different sensors like LiDAR, IMU, and cameras. And something that will be more realistic too will be to incorporate more dynamic obstacles like cars moving along the way, maybe bicycles, other pedestrians that will make the environment a more realistic one.
Thank you.